Hello and welcome. In this video, we'll walk through a classic electricity problem involving a light bulb. Our goal is to understand how the concepts of power, voltage, current, resistance, and energy relate to each other in a practical circuit. By the end of this session, you will be able to 1. Calculate the current in a simple circuit. 2. Determine the resistance of a component. And 3. Calculate the total electrical energy consumed over a period of time. So, let's dive into the problem. Here's the problem we'll be working with. It's a great example for connecting a few key electrical concepts. The first step in any problem like this is to identify what we know. This helps us see which tools or formulas we'll need to use. First, the problem states the light bulb has a power rating of 400 W. This is a measure of how quickly the bulb uses energy to do its job, which is to produce light and heat. Second, it tells us the bulb is connected to a 240-volt supply. The voltage, or potential difference, is the push that gets the electric charges moving through the circuit. It's crucial to understand these terms. Power in watts is the rate at which work is done or energy is transferred. Voltage in volts is the electric potential energy per unit of charge. In simpler terms, it's the electrical pressure. Now, let's tackle the first part of the problem. We need to calculate the current drawn by the bulb. So our goal is to find the current, which is represented by the letter I. The key here is to find a formula that connects the quantities we know, power P and voltage V, to the quantity we want to find, current I. A fundamental equation in electricity does exactly this. Power equals voltage times current, or P equals V times I. This formula tells us that the rate at which energy is used depends directly on how much push the charges have, and how many charges are moving per second. Power is the product of voltage and current. We know P and V, but we want to find I. So we need to rearrange this formula to solve for I. If P equals V times I, then to get I by itself, we can divide both sides of the equation by V. This gives us current equals power divided by voltage. Let's review that. We started with the power formula, P equals Vx, and rearranged it to solve for the current, I equals P over V. This is the formula we'll use. We now have the formula and the numbers, so let's substitute them in and calculate the current. Our rearranged formula is I equals P over V. We're given that P is 400 watts and V is 240 volts. Plugging these values in, we get I equals 400 watts divided by 240 volts. Performing this division, 400 divided by 240 gives us approximately 1.667. Since we are calculating current, the unit is amperes, or A. A ampere is the standard unit of electric current. It represents the flow of 1 coulomb of charge per second. So, 1667 amperes means that about 167 coulombs of charge pass through the bulb's filament every second. For our final answer, we can round to a reasonable number of significant figures, which gives us 1.67 amperes. So, the current drawn by the bulb is 1.67 amperes. Great work! We have successfully used the power formula to find the current, achieving our first learning objective. Let's move on to the second part of our problem, calculating the resistance. Our goal now is to find the resistance, represented by the letter R. Resistance is a property of a material that opposes the flow of electric current. In an incandescent bulb, the filament's resistance is crucial because the energy lost due to this resistance is what heats the filament up to incandescence. To find resistance, the most famous formula in electricity comes to mind: Ohm's law. Ohm's law states that voltage equals current times resistance, or V equals I times R. This law establishes a direct relationship. For a given resistance, the current is proportional to the voltage. Double the voltage, double the current. It's the most fundamental law for analyzing simple circuits. Just like before, we need to rearrange this formula. We know V and I from our previous calculation, and we want to find R. To solve for R, we divide both sides of the equation by I. This tells us that resistance equals voltage divided by current. So R equals V over I. So we've rearranged Ohm's law. Let's recap. R equals V over I. This is the formula we'll use to calculate the resistance. We're ready to substitute our values into the Ohm's law formula to find the resistance. Our formula is R equals V over I. We know V is 240 volts, And from our first calculation, we found the current I to be approximately 1.667 amperes. Now, it's generally best practice to use the more precise value for intermediate calculations to avoid rounding errors. So we'll use 1.667A. This gives us R equals 240 divided by 1.67. Notice that the units are volts divided by amperes. Volts per ampere is the unit of resistance, which is called an ohm. When we perform this division, we get approximately 143.99 ohms. The symbol for ohms is the Greek letter omega. Rounding to 3 significant figures, we get 144 ohms. So, the resistance of the bulb's element is 144 ohms. We've now successfully applied Ohm's law to find the resistance, meeting our second learning objective. It's also worth noting that we could have used another formula. Power equals V squared over R. Let's quickly see how that works. Sometimes there's more than one way to solve a problem. Let's look at an alternative method for finding the resistance, R. The power formula, P equals VC, can be combined with Ohm's law, V equals IR, to give us two additional power formulas. First, we can substitute IR for V in the power equation. Let's write that out. P equals V times I. If we replace V with IR, we get P equals IR times I, which simplifies to P equals I squared times R. This is a very useful formula. Alternatively, we can substitute V over R for I in the power equation. Starting with P equals 6C again, if we replace I with V over R, we get P equals V times V over R, which simplifies to P equals V squared over R. This formula uses only power, voltage, and resistance, which is perfect for our problem. So we have a formula, P equals V squared over R, that directly relates the two variables we were given at the start, power and voltage. We can use this to solve for resistance, R. Now let's use the alternative formula, P equals V squared over R, to find the resistance. Our alternative formula is P equals V squared over R. We know the power P is 400 watts and the voltage V is 240 volts. Plugging these values into the formula, we get 400 equals 240 squared, all divided by R. Now we need to rearrange this equation to solve for R. We can multiply both sides by R and then divide both sides by 400. This gives us R equals 240 squared, divided by 400. Let's calculate the numerator first. 240 squared is 57,600, so the equation becomes R equals 57,600 divided by 400. Performing this division gives us exactly 144 ohms. This confirms the answer we found using the other method. So, the resistance is 144 ohms. This demonstrates that often in physics problems, there's more than one path to the correct solution. Knowing these different formulas gives you flexibility. We've arrived at the final part of our problem, calculating the total energy dissipated by the light bulb. Our goal is to find the energy, represented by the letter E, over a specific duration of time, t. The problem states that the bulb operates for 1.5 hours. Time, t, is 1.5 hours. This brings us to a new concept. In physics, energy is often defined as the ability to do work. In this electrical context, it's the work done by the electric field to move charges through the circuit. It's also known as electrical work. We also need to remember the relationship between energy and power. Power is defined as the rate at which energy is transferred or dissipated. So, power equals energy divided by time, or P equals E over T. This means that power tells you how fast you're using energy. A 400-watt bulb uses energy 4 times faster than a 100-watt bulb. To find the total energy used, we need to rearrange this formula. We know P and T, and we want to find E. By multiplying both sides by T, we get that energy equals power times time. So, E equals P times T. This is the formula we will use. There's a crucial point to remember for this part. Physics formulas are designed to work with consistent units, usually the SI units. The SI unit for power, watts, corresponds to the SI unit for energy, joules, only if the time is measured in the SI unit for time, which is seconds. So even though the problem gives us time in hours, we must first convert it to seconds before we can use the formula E equals P times T. Let's convert our time, 1.5 hours, to seconds. First, we convert hours to minutes. 1.5 hours times 60 minutes per hour equals 90 minutes. Next, we convert minutes to seconds. 90 minutes times 60 seconds per minute equals 5,400 seconds. So 1.5 hours is equal to 5,400 seconds. This conversion step is absolutely essential. Using hours in the formula would give a result with incorrect units and an incorrect magnitude. Always check your units. Now that we have all the values in the correct SI units, we can calculate the energy dissipated. We'll use our formula E equals P times T. We know the power P is 400 watts, and we just calculated the time T in seconds to be 5,400 seconds. Substituting these values, we get E equals 400 watts times 5,400 seconds. Multiplying these two numbers gives us 2,160,000. And since we used SI units, our answer for energy is in joules. A joule is the SI unit for energy. A joule is equivalent to 1 watt-second. So 2,160,000 joules is the total energy dissipated by the bulb over 1.5 hours. However, the problem has a final instruction. We need to express our answer in megajoules. The prefix mega means 1 million, so 1 megajoule is equal to 1 million joules. To convert from joules to megajoules, we divide by 1 million. 2,160,000 joules divided by 1,000,000 equals 2.16 megajoules. So, the energy dissipated by the bulb is 2.16 megajoules. We've now successfully calculated the energy, meeting our third learning objective. Let's quickly recap our journey through this problem. We started with a word problem and broke it down into solvable parts. First, we identified the known variables and the quantities we needed to find. The problem gave us power equals 400 watts, voltage equals 240 volts, and time equals 1.5 hours. We needed to find current I, resistance R, and energy E. For part A, the current, we used the power formula, P equals Vx, rearranged to I equals P over V. This gave us a current of 1.67 amperes. For part B, the resistance, we used Ohm's law, V equals IRR, rearranged to R equals V over I. Plugging in the values, we found the resistance to be 144 ohms. We also saw an alternative solution using R equals V squared over P, which gave the same result. For part C, the energy, we used the power-energy relationship, E equals P times T. Crucially, we converted time to seconds and then calculated the energy to be 2,160,000 joules, which we then converted to 2.16 megajoules. I hope this detailed walkthrough has been helpful. You now have a solid framework for solving problems involving power, voltage, current, resistance, and energy. Thank you for watching.